Hello, hello. Let's welcome you again in this video lecture series for SCD. Let's have review of last lecture. What we have seen is, see, the screen showing FT. It means we had a discussion up to FT. Is it? Okay, let me enlarge the screen and finally we are here. See, this was the last point. So that was AI. Basically, we have derived the current gain. This current gain, short circuit current gain, is it, at higher frequencies, that's what, and we derive that HFE divided by 1 plus JF divided by F beta. So is finally, while in the journey of getting AI, we have derived F alpha, F beta, HFE, everything. Now after that, one important parameter is that FT, or threshold frequency, that we need to discuss. See, if you started studying a datasheet of a transistor, see, basically now I am talking about datasheet of BJT. So when you observe datasheet of BJT, what you will find? You will find VCE, then IC, then HFE. Different columns are there. So in the datasheet, the last column is FT. So that last column FT, what it shows? It shows a gain bandwidth product. Gain multiplied by bandwidth. Is it? That's what that FT is. See, let me write the equation again. For the current FE, F divided by F beta. Is it? Now this current gain, see, when you increase the frequency for the BJT, then the current gain approximately becomes voltage gain. Is it? So at higher frequencies, look at this, at higher frequencies becomes AB about. So that whatever current gain, you can treat same as a voltage gain. Is it? So as frequency increases, we have seen as frequency increases, the voltage gain or the current gain start decreasing. Is it? So when the current gain start decreasing, the frequency, look at this, the frequency at which that AI becomes unity, that frequency is your FT. Right? The frequency at which short circuit current gain of an amplifier becomes 1, becomes unity, that frequency is called FT. That is the last column from transistor data sheet. Is it? It means what I can say? I can say that at F is equals to FT, that is at the frequency at F is equals to Ft, that AI will be equals to 1. Is it not? The frequency at which current gain is equals to 1, that frequency is called Ft. Is it? So it means I can modify the above equation. What is the equation? See, equation of AI. Let me modify the equation, and then the equation becomes at F is equals to Ft, F is equals to Ft, AI will be, so AI will be 1, then that AI, that is 1, is equals to HFE divided by, now it will be Ft divided by F beta. Look at this, Ft is still there. You observe it, then what you will find? You will find that Ft divided by F beta, that ratio is very, very greater than 1. So that's why clearly written HFE divided by only Ft divided by F beta, where Ft is gain bandwidth product. Bandwidth product. What is that? F beta we have seen. F beta is what? Beta is a higher cutoff frequency. Higher cutoff frequency. Higher frequency, we refer it as an FH. But as it is a pi module, we have given a different notation for that higher cutoff frequency. We have referred it as a F beta or FHFE. But simply what it is a higher cutoff frequency. Is it? As you frequency higher cutoff frequency, it means the frequency at which gain drops to minus 3 dB. That is the significance of FT, the frequency at which short circuit current gain becomes 1. Is it? Now from this equation, look at the above equation. I can write Ft divided by F beta is Ft is to HFE divided by F beta, sorry, multiplied by F beta. It means what is that HFE? Look at the equation of Ft. This HFE is nothing but gain. At higher frequency, current gain is equal to voltage gain. No matter. Higher cutoff frequency. And one thing we know, higher cutoff frequency is it? Generally you write for audio amplifier. Look at this. Those who don't understand why I am writing FH is approximately bandwidth, then for them let me take an example. For audio amplifier, the ratio of audio amplifier 20 Hz to 20 kilohertz. What does it mean? It means the lower cutoff frequency is and the higher cutoff frequency is 20 kilohertz. So what is the bandwidth then? Bandwidth is equals to 20 kilohertz minus 20. So that isn't approximately equals to 20. अब इतने बड़े नंबर से इतना छोटा नंबर अगर सब्सट्रैक्ट हो जाएगा तो obviously the value will be approximately बड़ा number, is it? So that's why I said that bandwidth is approximately. So for any amplifier, bandwidth is approximately higher cutoff frequency. So that's why I'm writing this bandwidth. So it is basically what? By bandwidth. So that's why this T is called gain bandwidth product. Got the simple consideration? It is a gain and bandwidth product. Is it? Now, see, if it is a common emitter amplifier, we have written that Ft is equals to HF multiplied by beta. Now, for common base amplifier, here it will be HFB multiplied by F alpha. Yes, it is an obvious thing. For common emitter, it is beta. For common base, it is alpha because beta is so F beta, that is beta cutoff frequency for CE, alpha cutoff frequency for CP. That was the only and smallest point that we missed out. Is that when we start with the already we started. No, we had a separate lecture about the data sheet or specification sheet of BJT. In that, I told you that parameter Ft. When we start with frequency response, you will come to know about that Ft. Now here I will tell you what's the significance, how to consider that last parameter, how to consider that last column of your data sheet. Is it? But before that, let me plot everything on a graph. Is it? So how? Let me take a graph. Okay, let me take a shape and okay, XY plot. That is quite okay. Look at this. This is what is there on x-axis. On x-axis, I have. Look at this. On x-axis, obviously there is a frequency, and on y-axis there is current gain, short circuit current gain. Is it? Somewhere here the graph goes on. Look at this. Maybe this is the graph actually. At higher frequencies, we know that look at this. At higher frequencies, gain decreases. Yes, that's what gain is decreasing. So at higher frequencies, the gain is current gain or voltage gain, no matter, both becomes same. So I will write here HFE. So this level is what my HFE. This is current gain. Is it? So beta is a small signal parameter. Is it? HFE is a current gain at lower frequencies. But we found an equation of HFE. GMRB is nothing but your HFE. So instead of writing HFE, you can write GMRB. It becomes equivalent to HFE. So that's why I'm writing HFE clearly. Now see, what is F beta? The frequency at which gain is that. So means minus 3 dB means what? Is nothing but 0.707. Is that 0.707? So if this is HFE, then I will write here somewhere. Yes, now this level is, I will mark it as 0.707 of HFE. Okay, draw a line from that wherever it cuts to the graph, and this is what your F beta. Look at the beta cutoff frequency. The frequency at which gain decreases to minus 3 dB. Yes, this part is done. Right. Now my intention is not to plot only F beta, I want Ft also. Now what is that Ft? Ft is the frequency at which that AI falls to 1. Now if this value of AI at this point, okay, let me change the pen. At this point AI is equals to HFE. At this point AI is equals to 0.707 of HFE, that is minus 3 dB. Right. Here I will write minus 3 dB. Now I want Ft. Right. If I want Ft, then what is that Ft? Ft is the gain at which, okay, let me change the pen again. The value or the frequency at which the AI value becomes 1. Okay, this is what the AI value, which is 1. So now let me draw a line from here. This line, somewhere it cuts to the graph, and this is what my gain and bandwidth product Ft. Agreed? Is it? So this is all about common emitter amplifier and its frequency graph. What will happen if I plot a common base graph on the same thing? For common base, we know that HFB, look at this, let me change the pen. This HFB is always less than 1. HFB is less than 1. So as of now we have started, yes, it is less than 1. So let me write it is HFB. This level is HFB. This level, it has to decrease. Okay, see, it is decreasing. Yes, it is. Now what is alpha cutoff frequency now? Alpha cutoff frequency is 0.707 of HFB, as like beta cutoff frequency. So somewhere here I will mark it as a 0.707 of HFB. Okay, and now from that I have to draw a line. Where it cuts the graph. Okay, somewhere here it is cutting your HFE graph. So now this is what my F alpha. Look at this, F alpha and F beta. In between I have gain bandwidth product. I think that much work is sufficient on the same graph, because if I draw some more lines, obviously things will become confusing. Is that? So that much is okay. This is what a graphical representation. Graph of F beta, F alpha, and even Ft product. I told you why it is called gain bandwidth product. The frequency at which AI falls to 1 or AI is equals to 1 is what your Ft. Is it? That is gain bandwidth product. Is it? Now practically when you are working with the CE amplifier in lab, so what is the use of that Ft, or how can I read the value, how can I assume the value, how can I interpret the value of Ft? Is it? Just assume that you are designing an audio amplifier. See, assume that it is an audio amplifier, simply BJT based audio amplifier, and you're using a transistor call it as BC547, assume that, and that transistor having HFE is equal to 300. I'm using a transistor which has HFE is equal to 300, is it? And I'm designing audio amplifiers. So if it is an audio amplifier, then what will be the frequency range? Simply 20 hertz to hertz. So this is value of HFE, that is what my gain is, current gain, and this is higher cutoff frequency. It means it is my bandwidth. What will be the gain and bandwidth product? 300 multiplied by kilohertz, that is 20,000. Is it? Let me check what the number is. Let me calculate it. It is, let me write it exact number, 300 multiplied by 20,000. It will be 6 mega. What happened? 6 multiplied by 10 raised to 6 megahertz. That is what gain bandwidth product. Gain bandwidth product means I am talking about FT. So value of FT is now, if the transistor that you have selected which has HFE 300, that's what I'm talking about. If that transistor has F beta less than 6 megahertz, then what will happen? Then you will get a frequency response. Look at this, you will get a frequency response like frequency decreases at lower frequencies and you get a flat frequency response. Your gain will never fall at higher frequencies. This is what you will get practically. If your FT of a selected transistor is less than 6 megahertz. So if your FT of selected transistor is less than 6, obviously you will get a nice shift that you will get decrement at the low frequency and you will get decrement at the higher frequency. That is what perfect. I didn't say this graph is wrong. No, this is a correct, but this is 100% correct. Is it? So even at the time of practical frequency response, something like this, don't think it is going wrong. Things are going right. Just there is a problem with the gain and bandwidth product. The gain bandwidth product, you will get a nice graph like this. Is it? So it's not mandatory that all the time gain has to decrease at the higher frequency. If it is not decreasing, don't worry at all. It's not your problem. It's not your circuit bug. Basically, it's a factor of FT that you need to check for a particular transistor. Is it? So this is what all about FT that I wanted to tell you. Is it? So the special small session that I have conducted for this gain bandwidth product. So okay, I'll be very happy to tell you that we have finished this chapter, the chapter number 5 from your syllabus. We are finished with. So maybe I will conduct a separate session to solve some numericals related to this higher frequency response of BJT. Is that? So next time we'll meet to solve the numericals on the same chapter. Okay, till then, thanks a lot.